So in the last lecture, we stopped at this location. What we did was we considered a simple mixture right? We considered a simple mixture of N1 molecules of type 1 and N2 molecules of type 2, and we made a mixture. And the condition for miscibility is that free energy mixing must be negative. And then we went ahead and built a simple lattice theory with the assumption of a random mixing. And we also took the volume of each molecule of type 1 to be comparable, same as the volume of one molecule of type 2, right? And then based on this, which is same as a volume of a lattice site, and then we assumed there is going to be interaction energy between 1 and 2, nearest neighbor interaction energy to be epsilon 1, 2, nearest interaction energy between 2 and 2 is epsilon 2, 2, nearest neighbor interaction energy between 1 and 1 is epsilon 1, 1. Based on this, we derived, right, the following expression. We derived delta Fm by Kt is this blue term, which is coming from entropy of mixing, and there's a red term, which comes from delta Em. And here, please notice, N1 is number of molecules of type 1. N2 is number of molecules of type 2. And N0 is a total number of sites in the system. And phi 1 is site fraction, because since the volumes are the same, we also call it to be volume fraction. Volumes of all units, all lattice cells are taken to be the same. Phi 1 is also the volume fraction or site fraction in the lattice case. Phi 2 is a volume fraction of component number 2. And in the chi is we call chemical mismatch parameter, right? Which is given like this. Chi is 1 over temperature, the way it is defined, 1 over temperature. Z is a number of order unity. It could be 5, 6. It's a coordination number for the lattice. And then epsilon 1, 2 is the nearest neighbor interaction energy between 1 and 2. And similarly, epsilon 1, 1, epsilon 2, 2, between 1 and 1 and 2 and 2. So although we had 3 interaction parameters, in this lattice theory, all those 3 interaction parameters come together as a group and is given by the square bracket. Okay, and apart from 1 over temperature. So that's our chi parameter. And today I'm going to say that chi parameter is the same as Flory-Huggins chi parameter for polymer solutions and polymer blends, which I'm going to show today. I'm going to make a statement to that effect. But already, even for small molecular mixtures, that chemical mismatch parameter comes about. Okay, that's where we stopped. Now, what I like to do today is to take that expression and understand this a little better. Okay, that's what I'm going to do. Okay, how do we do this? I'm going to write at the top once more. So delta Fm by Kt is equal to N1 log phi 1 plus N2 log phi 2 plus there's a chi N0 phi 1 and phi 2. So this is coming from delta Em, and this is coming from minus T delta Sm. And as I've already argued, phi 1 is less than 1. Logarithm of some number which is less than 1 is negative. The N1 is of course positive. Similarly, phi 2 is less than 1. Therefore, logarithm of phi 2 is negative. Therefore, this blue term is negative. The red term could be anything. It could be positive, negative, maybe 0. It could be anything. when I say it can be anything, that depends on these relative values. Whether 1 and 2 like each other or hate each other in comparison with 1 and 1 liking between themselves and 2 and 2 liking between themselves. Compared to the relative attractions of individual components, if 1 and 2 like each other or don't like each other, the chi can be positive or negative, or they can even compensate. Chi could be some arbitrary number. Right? Now let's look at the consequence of some of these possibilities. Okay, again, once more, I want to write it again here. Chi is equal to Z divided by K dt epsilon 1, 2 minus half epsilon 1, 1 plus epsilon 2, 2. Okay. Let's consider a case, for example, a situation where I'm plotting 1-2 interaction. 1-2 interaction, and this is my energy. So interaction energy as a function of distance. Okay, R is distance, this is interaction energy, let's say. Typically, as you know, when two units, 1 and 2, come very close, they don't like it, they cannot sit on top of each other. So this interaction energy will be huge. Let's say it looks like this for 1-2 interaction. Let's say, let's give some number. Okay, so this number, right, this is 0 minus this number, I'm going to call it to be epsilon 1, 2. Okay, that's the meaning of this epsilon 1, 2. Remember, epsilon 1, 2 is the interaction energy between two neighbors when they are sitting together. So that is the value. In general, it will be more like a Lennard-Jones or van der Waals type interaction with the exclusive volume interaction, right? A repulsive interaction. Shape would be like this. Let's call this epsilon 1, 2 to be like that. Okay. Let's say as an example, just to show as an example, let's say epsilon 1, 2 is minus 10. Just as an example, for example. Similarly, let's look at 1-1 interaction. When you do 1-1 interaction, let's consider the situation. Again, this is U of R versus R. Let's consider a situation, this is 1-1 interaction. Let's consider a situation where it looks like that as an example. So this is epsilon 1, 1. Okay, let me assume epsilon 1, 1. Give me a number. I can choose anything. Since I drew this to be weakly attractive compared to this, maybe I'll write this to be say minus 2, say for example. Similarly, let's look at the 2-2 interaction. Okay, this is U of R versus R. Again, let me take, just for the argument's sake, let's say like that. So epsilon 2, 2. Let me assume epsilon 2 is equal to say minus 4. Say, let's say some choice like this. If that's the case, let's look at the chi value. Because notice that it's epsilon 1, 2, epsilon 1, 1, epsilon 2, 2 are negative, right? So let's take this case. This gives me, right, gives me what chi is. Tell me what chi is. Chi would be, so here is a minus 10. Here is a minus 2, minus 4. So the minus is 6 divided by 2 is minus 3 times minus 1, that's a plus 3. And then here I have a minus 10. So this turns out to be, right, turns to be negative. This comes to be negative, right? This is 4 plus 2 is 6, divided by 3, this is 10. So this becomes more important than the one, chi is negative. If chi, for this particular case, if chi is negative, what happens is this, already due to entropy of mixing, the free energy change is negative. So that's favorable for mixing. And then for this particular case where 1 and 2 love each other compared to themselves, like compared to 1-1 interaction and 2-2 interaction, 1-2 interaction is more favorable because it is a higher gain in energy when they come together. That means that, but that means that the polymer, the component 1 and component 2 like each other. That means they are going to be miscible. So in this particular case, this energy of mixing or enthalpy of mixing right? It's a negative. If this is negative, then we get miscibility clearly because delta Fm will be negative. Therefore, right, what we conclude is if chi is negative, we get miscibility. The mixture, the component A and component B are miscible. Okay. Now let's consider a case where the other way around. Suppose, right, if chi is very positive, chi is, imagine a situation quite positive, large and positive and large, what will happen? Okay, if this is very large, that can happen if this is epsilon 1, 2 is so small compared to epsilon 1, 1 and epsilon 2, 2. Because if these are large numbers, right, which are negative in number, they're large, and then with the negative sign, this will become positive, which is going to be overwhelming this interaction between 1 and 2. If that's the case, we'll get no miscibility. Right? There will not be any miscibility. Immiscible. Okay, that will happen. But somewhere, suppose, on the other hand, suppose if chi is positive but small, then you can have miscibility. So this is positive, chi is positive, but this term is so much negative that this will not be able to compensate for this negative term to make it immiscible. In that case, this term is going to dominate over this. If chi is small but positive, then you'll have miscibility. Okay, so this suggests there is this means, right? This implies there is a chi critical, okay, which separates between miscibility and immiscibility. Between miscibility and immiscibility. Please notice, we did not say anything about polymers here. We are talking about small molecular mixtures or metallic alloys. One kind of a metal with another kind of metal. Suppose I'm trying to make brass, for example, right? Right. So this is one of the fundamental theories that we use in trying to understand how components can mix. In the literature of metallurgy, as well as solid state physics, this theory is called Bragg-Williams theory. This is a century-old theory, Bragg-Williams theory, for small molecular mixtures. Okay, let me summarize once more again. What we did is we took small molecular mixtures and then we got this free energy expression. And the chemical mismatch between component 1 and component 2 is captured by this parameter chi. If we can estimate chi or measure chi, right, when they're right, if you can measure it somehow or calculate it, then we are in a good position to tell when this mixture is going to be miscible and when this mixture is not going to be miscible. Because we can use this free energy, we can say ourselves when this delta Fm by kT is negative. It has to be negative. This is a negative quantity. This can be positive, negative, small positive, large positive. Based upon that knowledge, knowing this chi, right, then we'll be in a position to determine the condition for miscibility, right? So now let me move on to a polymeric system. So instead of looking at simple molecules, small molecular mixtures, I like to look at the following situation. suppose I have, right, N1 chains, molecules, of course, each with capital N1 segments. Okay. Then I mix that with, I try to mix that with N2 chains, each with N2 segments. Okay. And that gives me, if I make it, when I make it, I'll get a blend, polymer blend. Right. And the question is, can I make it? That's the question. And as you know, right, the N1 chains are like this, and N2 chains are like that. And that's what I'm trying to do. This means I will have 1-2 type interaction between blue and red. I will have 1-1 type interaction between blue and blue, and 2-2 type interaction between red and red. So I'll still have the same chemical mismatch parameter, chi parameter. Okay, let's do the calculation. And now it's easy to do, but in the interest of time, I'm just going to give the answer. Okay, the answer is the following. Okay. Delta Fm by kBt, free energy of mixing. It also has two terms, right? Entropy of mixing term, which is N1 log phi 1 plus N2 log phi 2. What is phi 1 and phi 2? Phi 1 and phi 2, phi 1 is equal to volume fraction of polymer of type 1. That is N1, capital N1, divided by N1, capital N1, plus N2, N2. Okay, I can write N1, capital N1, plus N2, capital N2 is equal to N0, total number of sites, just like what we had before. Okay, similarly, phi 2 is equal to N2, capital N2, divided by N0. And once again, because N1 plus times N1 plus N2, capital N2 is equal to N0, I could rewrite this to be 1 minus phi 2, phi 1. So I could also write it. This is for entropy of mixing. Please notice, N1 is a number of chains, and a little N2 is a number of chains of type 2. Now let's see what happens to the energy. If you do the calculations, the energy turns out to be chi N0, phi 1, phi 2. Okay. Please notice that this equation is exactly the same as this equation. Identical, right? N1 is the number of molecules here of type 1. N2 is the number of molecules of type 2. Same thing. N1 is the number of molecules of type 1. Number of molecules of type 2 is N2, and exactly the same expression. This we call Flory-Huggins theory. We get the same expression, except the meaning of phi 1, phi 2, or in terms of number of segments. Phi 1 is total number of segments of type 1 divided by volume, which is the total number of sites in the lattice. N2, capital N2 is total number of segments of type 2, okay? And N0 is the total volume of the system. So that's it. This is really remarkable, right? Under these circumstances, we call chi to be Flory-Huggins chi parameter. But once again, what are the assumptions? The assumptions are, right? The assumptions are random mixing. Right on. The assumptions are random mixing. That's a key assumption. And then, of course, segment volume are the same, right? Random mixing and segment volumes are the same for convenience of arithmetics, right? But the important assumption is the things are all the segments are randomly mixed. If you do that, you get the same results. Okay, so therefore, all the things that we talked about before can be used, implemented in trying to get the condition for miscibility. So basically what I'm trying to say is in small molecular cases, when chi is large, then it will be miscible. Now let's look at the situation for our polymer case, polymer blend case. Okay, the same equation, but now let's look at the consequence of capital N1 and capital N2, because we are trying to mix two kinds of polymers, right? How do we do this? And we do that in the following way. So taking the same expression, what I'm going to do is, let me look at a per site. Maybe I'm going to rewrite it again. Delta Fm by kBt, right? N1 log phi 1 plus N2 log phi 2 plus chi N0 phi 1 phi 2. So let me divide this by N0. Divide by N0. That is volume. That means the delta Fm by kBt per site, per one site, or density, if you like. This is free energy of mixing density divided by volumes. That's equal to, right? Let's do this. N1 by N0. I'm doing my N1 by N0. Going back here, N1 by N0. This is denominator is N0. N1 by N0 is phi 1 divided by capital N1. So I get phi 1 divided by capital N1 log phi 1. Similarly here, plus N2. N2 divided by N0 is phi 2 divided by capital N2. So this becomes phi 2 divided by capital N2 log phi 2. And then plus chi, N0 goes out because I'm dividing by N0, chi times phi 1 times phi 2. That's what we have. Okay, instead of looking at per site, let's look at per molecule. Right? If you do per molecule, what do you have to do? And before that, maybe what I will do is, for example, consider a symmetric blend. When I say symmetric blend, I mean N1 is equal to N2. N1 is equal to N2. Okay, let me say that's equal to, that's equal to N. Okay, it's a symmetric blend to make my argument, because we are going to have a very important message in terms of comparing this expression for the polymer situation with a small molecular mixture. The equations are the same, identically the same, but when we have phi 1 and phi 2, we have phi 1 and phi 2, right? And we'll see exactly what the consequence is. Since capital N1 is equal to capital N2, right? I'm going to look at delta Fm per molecule. Delta Fm per molecule. Because each molecule is having capital N segments. Therefore, what I have to do is, this is per site. This is the expression. So now what I have to do is, I take this expression, multiply by capital N. N1 is capital N, N2 is capital N, right? So I will get, this is equal to phi 1 log, oh, I'm sorry, made a mistake. Okay, so here, sorry. That's phi 1. Phi 1 log phi 1 plus phi 2 log phi 2, right? And then we have plus chi n, and then I have phi 1, phi 2. Suppose I'm trying to, there is a huge message coming out of this. Please go back to the simple mixtures that I summarized before. Here, what I had is, right, per a molecule, right, we will have chi. If I go in here and divide it by per site, that will be my volume, right? Divide by volume, that means the delta FM, that's per site. That means per molecule, because small molecule, there is no degree of polymerization, small molecule. Then it will be phi 1 log phi 1 plus phi 2 log phi 2 plus chi times phi 1 phi 2. So we will have this expression, phi 1 log phi 1 plus phi 2 log phi 2 plus chi times phi 1 phi 2. Because obviously when capital N is 1, when capital N is 1, it's a small molecular system. We must get that result. So by polymerizing component 1 and component 2, suppose the molecular weights are comparable and the degree of polymerization is the same for these two components, then what we get is, instead of having chi, we have chi times n as a key variable. So small molecular cases, small molecules, so small molecular mixture, I have chi. Okay. A polymer chains, mixing, trying to mix polymer chains, I have chi n. Right? So going from small molecules to polymer chains, trying to mix, I go into chi n instead of chi. But please look at the implication of this. We already talked about there exists a critical chi, right? The critical chi is depending on how much this entropy mixing is. If chi is, right, chi is larger than this quantity, then it will become immiscible. If chi is larger than, but when you take polymers, since I'm having chi times n, it's very easy for that number to be very large because the equations are the same. If chi is large, then they won't be miscible. And naturally, in the polymer case, that the effect of chi is large because when you have polymerization, n is a large number, 100 or so. So even though you're going to have small amount of chemical mismatch between A and B, you can have huge value for chi, and hence there is a chance that they'll phase separate. So even in the delicate situation of a protonated polymer and deuterated polymer, they are chemically identical except for the protonation versus deuteration. You know, when you want to do neutron scattering, sometimes you do this, right? And then it is possible that a chi n, although chi is very tiny, the mismatch is very small, still chi n could be very large. And it is conceivable that you can have phase separation even in such a delicate system, delicately chemically different. But when you think of a different kind of polymers, immiscibility is easy to happen because this is a large number. It can be a large number. And here, phi 1 log phi 1 plus phi 2 log phi 2 is the same as before. Okay. So now what I like to do is, I like to now go to the next question of understanding polymer solutions. Right? Maybe you want to look at this and reflect on this a little bit. Right? And this is a good time to take a break before I launch onto the next topic. I want to implement this equation for polymer solutions where one component is solvent Second component is a polymer. First component is a solvent. Other one is polymer. That means capital N1 is equal to 1. Capital N2 is N, large number. Okay, that's what I'm going to do. June Fang, is this a good time to take a break?
Okay. Hello, Professor.
Yeah.
So let us have a 5 minutes break.
Yes.
Thank you.
So what I emphasized earlier was that as soon as you polymerize molecules of type 1 and molecules of type 2, then it's easy for them to be immiscible. Now, please remember that chi is 1 over temperature, right? Chi is 1 over temperature. So now instead of chi, now I have chi times n, which controls the condition for phase separation. This means the combination is chi is 1 over temperature, n over temperature. Therefore, degree of polymerization where temperature, right, is a key variable, key control variable for immiscibility, for polymer immiscibility. What does that mean? That means, therefore, n increasing, molecular weight increasing is equivalent to, this is same as equivalent to the temperature decreasing. Right? When I decrease the temperature, take chi parameter. When I go to chi parameter, small molecular cases, when I go to small molecular cases and decrease the temperature, chi becomes large. When chi becomes large, you'll have phase separation, immiscibility. This is called, we'll come back to this. This is called upper critical solution temperature behavior. We'll come back to this later in the next lecture, probably. So in general, according to this Bragg-Williams theory, if you lower the temperature, it is likely to phase separate, immiscible. The components will become immiscible. You can achieve the same thing, but keeping the temperature at room temperature, but increasing molecular weight. When you increase the molecular weight, then it will also become immiscible because the effective chi now becomes a large. Okay. Okay, given that, now let's go to polymer solutions. So right now, what I like to talk about is two-component polymer solutions. So I have, right, N1 solvent molecules. Where capital N1 is equal to 1 plus N2 polymer molecules where degree of polymerization is equal to N. Since the solvent has only N1 is equal to 1, I don't want to carry the subscript anymore, right? So this is what I like to look at. Once again, we use a lattice theory, right? We use a lattice theory. And then here is solvent molecules randomly placed, if you like, something like that. And the polymer polymer molecules, let's say, they take like this, and then go into the other dimension, randomly placed, etc., randomly placed, like that. And then other places are solvent molecules, something like that. Then we use the same important assumption, which is random mixing. Random mixing, that's a very important assumption. Second assumption is the volume of solvent is same as segmental volume, which is same as a volume of the site, volume of each site in the lattice. Okay, that is the assumption. If you do this, what do you get? You get exactly the same expression. Delta Fm by kBt is equal to N1 log phi 1 plus N2 log phi 2, and then plus chi N0 phi 1 phi 2. Now we need to define what phi 1, phi 2 are. Phi 1 is equal to N1 by N0, and phi 2 is equal to N2, capital N2 divided by N0, right? And of course, N0 is equal to N1 plus N2, capital N2. Is the total number of sites, because N1 molecules, there are total number of segments from the polymer. Oh, I don't have to write N2 anymore, right? Because that's N. And here also, I don't need to write, yeah. Okay. So exactly the same expression that we had in a Bragg-Williams theory, as well as in a Flory-Huggins theory. Sometimes it's possible to write, sometimes you can also, you will see in textbooks, you will also write in terms of per site. Okay, so this is the key expression, right? This is the key expression. I'm writing this repeatedly because I think you want to remember this, because this is bread and butter of polymer science and engineering. We use it all the time because you want to make new alloys, you want to see when they are miscible, when they're not miscible, et cetera, right? It's an important expression. Now, per site, that is density, delta Fm by kBt, and here is N0, then you know N1 by N0 is a phi 1. So this will be phi 1 log phi 1 plus N2 log phi 2. N2 divided by N0 would be phi 2 divided by N plus phi 2 divided by N log phi 2. And then I have the energy term, chi phi 1 phi 2. Okay. Sometimes you see this. Sometimes, some other times, for people write to be sometimes in books you'll see phi 2 is equal to phi, and of course phi 1 is equal to 1 minus phi, where phi is volume fraction of polymer volume fraction. Polymer fraction. That when you do this, what you get is, of course, very easy. This repetition, delta Fm by Kt is equal to phi 1 is 1 minus phi. Okay, I have 1 minus phi log 1 minus phi plus phi divided by n log 5, and then plus pi times 5 times 1 minus 5. Okay. They're all the same. This is the same expression. You can write it in so many different ways. This is for the total system, and this expression for this is the density. You are dividing by volume. Similarly, this is the density, right? So you need to be careful when you do your homework problems, or when you want to implement conditions. You have to be very careful about which equation you use. Please recognize that n0 is in the denominator here in these expressions. But this is a clean formula for the whole system. Okay, now let's look at the consequences of this. Once more, I want you to think about this, right? Please look at this expression again. When you look at per density, look at this expression. If suppose you increase the molecular weight more and more, then what I get is I get 1 over n, right? N is large. That means this term becomes very small, right? Similarly, even for the blend case, right? If I go in here, suppose you increase the molecular weights, N1 and N2, right? This is the denominator. If N2 is, say, 100, this will be weak. Capital N2 is, say, 100, 200, this will be weak. So what you do is when you polymerize them, you are making this blue term weaker and weaker. That means the driving force for miscibility coming from entropy is weakened by polymerizing them. Therefore, this interaction energy takes over miscibility and immiscibility. This becomes weaker and weaker. Now, in the case of polymer solutions, you have something in the middle, right? There is an entropy of mixing, which is blue term here. Coming from the polymer could be weak, but the solvent molecules, they are moving around. So there's an entropy involved with that. And that doesn't have to be small. So for small molecular cases, entropy mixing is quite important. When you polymerize both components, then entropy mixing could become weaker. For polymer solutions, it's something in between. All right. That means for small molecular mixtures, you need to have very high value of chi to make immiscibility. For polymer blends, you need a very small amount of chi to make immiscibility because this term is weak. Right? For polymer solutions, somewhere in between. So right away, even before we do calculations, put into a computer, make measurements, we have a very good understanding of what we need to do in terms of chemistry to make miscible solutions, to make miscible blends, or how do you play this game with the oligomers versus the polymers, right? Just, you get the big qualitative picture of how to play the game if you're interested in trying to mix things. Okay. Now, I like to look at the consequence of this expression. Okay. And let me tell you something that you already know to begin with. Okay. Suppose I have a system, right? And I just throw in some change in here and here. And then I throw in some change here and there. What will happen is this. The drawing that I'm making is, right? The drawing I'm making is a deliberate, right? But in reality, the system may not be looking like this. In reality, the system may, we do not know. It may so happen that, right, the blues may be here predominantly and reds may be there predominantly. Okay. So the thermodynamic parameter, thermodynamic quantity that it tells me whether a system is in equilibrium or not. In equilibrium, do I have this? Or in equilibrium, do I have this? In order to know the equilibrium conditions, what I need to know is the chemical potential of a particular component must be the same everywhere. Only if for the whole system, if the chemical potential of a component is uniform, then there is no driving force for them to move around, right? Until that condition is maintained, the system will evolve. I suppose I take in a beaker, I take a polymer, some powder of a polymer and throw it in a solvent, and then I mix it up, right? Right now, the chemical potential of the polymer is not the same everywhere. Similarly, the chemical potential of the solvent is not the same everywhere. But if I wait for some time, the system will evolve until the chemical potential of the polymer is same throughout the system, and chemical and solvent is the same throughout the system, whether there is going to be miscibility or immiscibility. Okay. Therefore, the key quantity that we need to do is we need to assess its chemical potential. Can you hear me?
Yes.
Oh, good. So what I was trying to tell is that there cannot be any chemical potential gradients in a system if the system is in equilibrium. So in order to see how, when the system is going to be in equilibrium and how the system is going to be in equilibrium, we need to calculate chemical potential, and we want to make sure the chemical potential of every component is the same throughout the system. Okay, how do we do that? And the chemical potential can be gotten from the free energy of mixing. For example, the chemical potential mu, let me write down mu I. I is the component. Chemical potential of, say, first component, in this particular case, it's solvent. Chemical potential of the first component for a given volume fraction of the polymer phi.
Professor?
Yes?
Can you share your screen?
Oh, you can't see it? I'm sorry. Oh, that's strange. I don't know what happened. Okay. Okay, so what I'm trying to say is that the system has to be maintaining equal chemical potential for every component if the system is in equilibrium. So I'm trying to, therefore, but the chemical potential is related to, as you know, from your undergraduate classes, it's related to the free energy. So if I take the mu1, say at the volume fraction of mu1 is chemical potential of the first component, in this particular case, solvent, right? In general, mu1 is chemical potential of the first component at some volume fraction phi2. With respect to a reference state, 1 is a solvent to say. That means, or for the pure component, phi2 will be 0. Mu1, phi2 is equal to 0. Divided by Boltzmann constant times the temperature, that's equal to, okay, the partial derivative of a delta Fm that we calculated by kBT with respect to number of molecules of type 1 by keeping temperature fixed and N2 fixed. Okay, that's a definition of chemical potential, right? And we know what delta Fm is. Either I'm talking about polymer solutions or a polymer blend, I know what delta Fm is, or even a small molecular mixtures, I know what it is. So I take this expression for a polymer blend or this expression for polymer solutions, this or this, whatever, right? Let's take this expression and I take the derivative with respect to N1, first derivative, that's easy to do. In a similar way, the chemical potential second component, which is mu2, so here this I is 1 and 2, right? Second component, at the volume fraction phi2 minus the value of the chemical potential for the pure component. For the pure component, so number 2, volume fraction is 1. So here, 1 divided by kBT is equal to same expression, d delta Fm by kBT dN2, keeping temperature fixed, N1 fixed. Okay, that's a definition of chemical potential. Okay, now it's an easy exercise, right? So I go to, say, for example, in general, I can go to this expression, this expression. This is a very general expression we had for polymer blends, for example. That's a general expression. And then I take the derivative with respect to N1. Please notice, this is a homework problem. You can work it out, right? You notice that N1 appears here, phi1 depends on N12, right? Phi1 depends on little n1, phi2 depends upon little n1 again. So you have to take into account all these things. If you can do the first derivative, if you do that, what you get is the following. Mu1, phi2 minus mu1, 0 divided by kBT is equal to, there is a blue term and a red term, right? The blue term comes from terms like this, and then there will be a red term. If you do this, what you get is the following, right? The answer turns out to be, in general, it turns out to be log 1 minus phi2, okay, plus 1 minus n1 by n2 phi2, and then from the red term, you'll have plus chi n1 phi2 squared. So this is, for suppose one is a solvent, right? One denotes solvent, this is chemical potential solvent at the volume fraction of the polymer, namely second component polymer. That means N1, capital N1 is 1, capital N2 will be N, for example. But I'm giving you a general formula. Similarly, for the second component, mu2 at phi2 minus mu2 at 1, phi2 value is 1 by kBT is equal to, again, the blue term would be log, right, phi2, it's symmetric, right, plus between 1 and 2, 1 minus n2 divided by n1, 1 minus phi2, and then the red term would be plus chi n2 1 minus phi2 squared. Okay. So these are general expressions, and I hope you'll use, this is all given in the handout. And I sent this PDF earlier today, right? You'll see these formulas there. Right? So if you want to consider mixtures, right, you can use these formulas. Now, what I'm going to do is, in view of the polymer solution I'm talking about, and I want to talk about a situation where capital N1 is equal to 1 and capital N2 is equal to N. That's what I want to talk about. So polymer solutions for polymer solutions, two components, right? Polymer solutions. There are only two components, solvent and polymer. All polymer chains are having the same molecular weight. It's a monodisperse. For polymer solutions, where N1 is equal to 1 and N2 is equal to N. Okay. Let's look at the chemical potential of the solvent. Mu1, right? Let's say phi2 minus mu1, phi2 is equal to 0. Phi2 is equal to 0 by kBT is equal to, let's go back and look at this, right? Log 1 minus phi2, and then here N1 is 1, N2 is capital N, and this N1 is equal to 1. So you get the following result. Log 1 minus phi2, right, plus, sorry, minus phi 2, yeah, plus, what do you get? 1 minus 1 over n phi 2, and then plus chi phi 2 square. That's what we get. So there's a full formula, very simple formula. And you'll realize that this kind of expression comes again and again in the polymer physics, whether we talk about gels, whether we are going to talk about crystallization from a mixture, from a polymer solution, right? Or when we have glasses, but we have some additives, and we'll see this expression again and again. So it is important that we master where these equations come from and what the implications are. Okay, how do I measure the chemical potential of a particular component, in this particular case, solvent? How do I measure this, right? And measuring chemical potential is difficult, but I can measure osmotic pressure, particularly for solutions. I can measure osmotic pressure. And there is a thermodynamic relation between osmotic pressure and chemical potential. So osmotic pressure of a solution, which I'm going to write, right? I'm going to write osmotic pressure. I'm going to use the symbol phi. And the definition of osmotic pressure in terms of chemical potential is pi times V1. I'll define in a minute what V1 is. kBT is equal to negative chemical potential phi 2 minus chemical potential 0 divided by kBT. So the negative of the chemical potential difference, this is the reference state. That's the chemical. The negative of chemical potential is given by the osmotic pressure. Here V1 is solvent volume of molecular volume of solvent. Volume of one solvent molecule. If you use a Boltzmann constant, it's a molecular volume. If you want to use a gas constant R, then that V1 would be molar value. Okay. So now I have an expression for mu1 by given this formula. Now the connection between osmotic pressure and that one is this. Therefore, I can write down what the osmotic pressure is. Okay. So osmotic pressure then pi V1 by kBT is equal to, I'm repeating myself, minus log 1 minus phi 2 minus 1 minus 1 over n phi 2, and then again minus chi phi 2 squared. So that's the osmotic pressure. And I hope you remember the discussion we had about osmotic pressure long time back, right? We had osmotic pressure. Where do we have osmotic pressure? Here. So we had an osmotic pressure discussion. Osmotic pressure of a dilute polymer solution. Dilute polymer solutions went to like osmotic pressure, in terms of simple arguments, it went like the leading term is concentration, 1 over molecular weight. Osmotic pressure will go like Fantova, ideal gas law, which is monomer concentration to a molecular weight or degree of polymerization. And the second term is a second virial coefficient times C squared. Please remember, second virial coefficient went like RG cubed by M squared. That means in terms of molecular weight dependence, it went like 3 nu minus 2, M power 3 nu minus 2. But also, RG for good solutions went like the extra volume parameter, half minus chi we talked about, right? That went like power 1/5. So they'll have 3/5 RG cube. A2 will also depend upon half minus chi here, right, as a prefactor. Okay, that's what we did. Now we return to the Flory-Huggins theory. What does it say? Let's check our backgrounds, right? I mean, we knew in dilute solution that's what it should be. But what does the Flory-Huggins theory say? So therefore, let me say for dilute solutions, let's work out for dilute solutions where phi2 is much smaller than 1, I need to look at the consequence of this expression. And I want you to remember, that means even phi2 is small, I have to expand this logarithm, right? So you know that, remember, recall log of 1 minus x is equal to minus x squared by 2 minus x cubed by 3, etc. So that's the expansion of logarithm when x is small. In that case, let's go back here, pi v1 by kbt is equal to, let's work it out, minus a log 1 minus phi 2. Okay, log 1 minus phi 2 will be minus phi 2. There's a negative sign here, so I write it down to be phi 2 coming from this term. And the next term is a minus phi 2 squared by 2. And then I have another negative sign. Therefore, plus half phi 2 squared, half phi 2 squared. And then I have another term, phi cubed by 3. I don't want to worry about it. The phi x is so small, phi 2 is so small. Let me not do this. But if I want to do other quantities like a gel compression, expansion, one has to think about that term. But for the particular purposes, we are interested only in the second variable coefficient, right? So, okay, I go back here, then I get minus phi 2 from this term. And then minus times minus is plus. I have phi 2 divided by n. And then I have a minus chi phi 2 squared. And of course, I'll write plus higher order terms, which I don't worry about. This is really fantastic, right? Because this phi 2 cancels with that phi 2. Phi 2 plus phi 2 minus phi 2. And the leading term is phi 2 by n. Right? This is equal to phi 2 divided by n. This is Fantor's law, ideal gas law. We recover that one. And then a plus, I have a half term here minus chi term there. Okay, so what I get is, right, what I get is half minus chi phi 2 squared. So this is where you talked about chi at the theta point, right? Phi 2, the second variable coefficient is 0. Okay, so this would be the second variable coefficient we define A2. So according to Flory-Huggins theory, A2 is equal to half minus chi, according to Flory-Huggins theory. So we claim, right, at the theta temperature, the second variable coefficient 0. That's what we talked about. So at the theta temperature, chi is equal to half. Okay, that's what we get from Flory-Huggins theory. But remember, this is not the same as what we had in dilute solutions. Right? Recall from rigorous calculations, we found A2 going like RG, right? RG cubed, right? Remember? A2 went like RG cubed divided by m square, in this case, n square. This went to like, if you remember, RG for good solvent, for example, it went to like, if you go to Flory's theory, it'll go like, right, 1/5, for example. Okay, 1/5. Sorry, V to the 1/5, N to the 3/5 for a good solvent. And where we said is half minus chi, right? V is equal to half minus chi. Therefore, we expected A2 to go like half minus chi power 3/5 times N to the, now you can work it out, 9/5, right? Minus 2 is a minus 1/5. That's what we got. See, we got the molecular weight dependence and also a different exponent here. Now, what the Flory-Huggins theory tells us, A2 Flory-Huggins theory tells us is A2 is simply half minus chi. Okay. Now the question is, why is there a discrepancy? I gave this as a homework problem to you, but you can I'll give you the answer, because if we are not collecting homework problem exercises, right? So I have to tell you the answer. The difference, the reason why the Flory-Huggins theory fails in dilute solutions. Therefore, Flory-Huggins theory fails in dilute solutions. Why is that? The reason is, you go look at the cartoon. If I have a dilute solution, right? If I have a dilute solution, one chain is here, another chain is going to be somewhere here. I cannot assume that everywhere the segments are present. This is what this means. Random mixing means that they can interpolate overlap everywhere. There is an average density. That is broken down, because as you know, in dilute solutions, there is a correlation length for the segmental distribution. There is a correlation length which is comparable to RG. That is not respected in the Flory-Huggins theory at the dilute solutions. Therefore, this is due to, because, why is it? Because fails, because random mixing assumption. This cannot be valid for dilute solutions. However, this assumption is okay, is applicable, valid, if concentration is greater than overlap concentration. If the chains are intermingling, if the concentration is higher than overlap concentration, then the random mixing assumption is a good one. In the case of polymer blends, polymer solutions, if you want to look at miscibility, making polymeric alloys, etc., we are going to be at a higher concentration of the polymer. That is what is practically interesting. Under those circumstances, it's okay to use the Flory-Huggins theory. Therefore, we shall use Flory-Huggins theory for higher polymer concentrations. Higher polymer concentrations, then it's okay to use. So right away, we need to have an appreciation of when we can use Flory-Huggins theory. We cannot, for example, you cannot make neutron scattering measurements of a diluted component. One component is a deuterated, for example, that's in a lower amount. You will not be able to, and then other is protonated. You will not be able to see any immiscibility if they are not randomly mixed, right? The concentration has to be high enough, right, in order to implement Flory-Huggins theory. Okay. Now, given this, what I like to do is I like to plot this osmotic pressure, given this caveat about when it's applicable or not. We know that if we do this, we get this, and there is some deviation between the real answer and Flory-Huggins theory, but then we rationalize why, and therefore we have some confidence that we can use this expression for higher concentrations. And that's what I'm going to do. I take this expression and with a pocket calculator, I'm going to plot it. I'm going to plot this osmotic pressure, right, versus phi2. And there are two important inputs I have to put. One is a chi value, I do not know in general, and n also is a variable. So I'm going to give some value of n, and I'm going to plot for that value of n. Let's say n is equal to 1,000. I'm going to plot osmotic pressure as a function of phi2 for different choices of chi. That's what I'm going to do now. And you can do this in your calculator too, right? So when I do this, I get something very interesting. So I go and plot a pi V1 by KBT. As a function of phi2. Let me say n2 or n is equal to 1,000. I'm plotting for this one. Okay. Let me choose some value. So I kind of intuitively know from this argument, the theta temperature is a chi being half, either from this argument or that argument. When chi is equal to half, that becomes 0, chi is equal to half, that becomes 0, right? And in fact, one of the discussions that we had, and Dija asked a question about this number. Normally, theta temperature is identified to be chi being half, and that's true independent of the rigorous result or this Flory-Huggins result. Typically in textbooks, you will see this definition for chi being half to be corresponding to theta temperature. In reality, that's the expression one has to use. Okay, so therefore, I like to look around chi around there, around half. I don't want to take chi to be 100 and look at what the plot is going to be. We can do it, but that's not going to be very useful. So let me plot for chi to be half. If I do this, what I get is the following. If I do this, I get something like this. This is chi is equal to half. What does this mean? This is chi is equal to half. What does this mean? This means, suppose I take a volume fraction phi to this number, and there is a pressure. Okay. Now, if I take osmotic pressure, if I take a higher value of polymer concentration, then there's an osmotic pressure. The system is stable. When you increase more and more of a polymer into my beaker, the pressure goes up. Okay, that's perfectly fine. But then disaster happens if now chi is something small, something higher. Suppose I take chi is equal to 0.54. This is 0.5. Suppose I take that, then what I get is the following result. It increases like this, then it goes like this. This is for chi is equal to 0.54. This is what the Flory-Huggins theory predicts. This is the osmotic pressure of a polymer solution for n is equal to 1,000. Solvent is component 1, that's volume of the solvent. Pressure, osmotic pressure is related to chemical potential of solvent. This is what we get. This is kind of very scary, right? Because why? It predicts some boundary, right? Some boundary, which I would write to be this between that point and that point. Look at this. When I increase the volume fraction of the polymer, the pressure goes down. This is not possible. When I add more and more material, the pressure cannot go down. When I add more material, right, pressure has to go up. Therefore, this is no. This is not acceptable. That means that the system will not be there. It is not possible at all to realize. So between this point and that point, I cannot have any stable system. Between this point and that point, I have an unstable situation. It is not possible, right? But on the other hand, if I'm in this branch, it is when I increase the polymer concentration, pressure increases. In this branch, when it increases the polymer concentration, pressure increases. But again, I cannot have negative pressure, right? But now I told you that going back to my initial comment today, the chemical potentials have to be the same. chemical potential component 1 should be the same throughout the system. Similarly, chemical potential component 2 must be the same throughout the system. So I go here. This is the chemical potential, related to chemical potential, right? That is, if I draw a line between this and this, the chemical potential will be the same. Here is a chemical potential here, a same value of chemical potential there. There is one phase with some volume fraction 5 to some number, another phase with the volume fraction, say 5 to different number. That means there are going to be two phases with the different volume fractions. They will have the same chemical potential. So instead of having only one mother phase, I'm going to have two daughter phases with the different concentrations. But if this and this one coexisting is okay for component 1. This coexisting with this one is okay for component 1. But at the same time, I also have to make sure the chemical potential second component is the same. When I take these two conditions together, what I get is there's only one horizontal line that is allowed out of all these possibilities. That horizontal line I'm going to draw here. Between this one, oh, sorry, I'll use a different color. Between this point and that point. That's the only thing that's allowed. This, let me call to be phi 2 prime. I call this concentration to be phi 2 double prime. Out of all these possibilities, only one unique combination for this chi, for that particular value of chi, I'll have two phases coexisting. There will be two phases that will be born, right? So, but in the middle, there will be an instability. Now, what I like to do then is, if I change the value of chi between half and 0.54, I get into a situation where there is some intermediate situation happens. If I go here, something like this. This value chi is equal to 0. Right? I know this now, 0.532. Okay? And if chi is larger than that, I will always have this region of instability. If a chi is smaller than that, I'll have no problem. Everything is miscible homogeneous, right? For every volume fraction, there's unique pressure. So there is a critical point. I'm going to call this to be critical for that value of n. There is a critical point, right? Above that value of chi, you remember chi becoming larger will lead to immiscibility. Then the homogeneous system breaks into two phases, two daughter phases. One phase will have this concentration, another phase will have this concentration. Okay, and I'm going to take 3 more minutes to summarize this. Okay, suppose I want to, maybe we can do this another time if it's too much information here. What I want to say is, I like to say that if I plot, say, chi, if I want to plot chi versus volume fraction phi 2, right? Between the green points, I have, let me write green point in here, green point there, right? And then between those two green points, that will be phase separating for chi is large enough. Between those two green points, there are going to be two red points. And this is a no. This is not allowed. No, unstable. Then if I lower the chi, I'll get a series of green points, and eventually we'll reach some critical value. Similarly, I'll have series of red points, something like this. So if I connect them, I'll get something like this. Okay, this is unstable. Okay, and if I connect the green points, I'll get the coexistence curve. This is coexistence curve. And below this point, below this special point, this point, which I call critical chi and critical volume fraction of the second component. Below this, I have homogeneous system. Okay, and I think I'm going to stop here. And I will address this issue in great detail in the next lecture. We'll devote a considerable amount of time. And I wanted to please think about the result that's coming from this. And we will meet next week and look at the implications of these things, what is happening in this region, what is happening in this region, et cetera, et cetera. And how do we determine chi critical? How do you determine phi 2 critical based upon the simple expression we have got, based upon this expression, or in turn based upon this expression. These expressions are simply based upon this expression. Based upon this, we are going to determine what we call phase diagram. Okay. I think in the interest of time, I think I should stop here, and I will review this once more. And hopefully, if you come up with some questions, that will be desirable. Okay, and I'm going to stop sharing the screen, and I'll take any questions if you have.